What we did last time was introduce a Gaussian free field. I remind you that the Gaussian free field on a lattice box was a Gaussian field such that you could write the density the sum over all edge variables, which is the same. Another way to discuss it or to represent it is that you have a bunch of independent random variables on each edge, and you condition it on the sum of every loop being 0. So it's a small exercise to convince yourself that these two descriptions are exactly the same. And I remind you also that by convention, every time I'll talk about the Gaussian free field in a box, I will mean with Dirichlet boundary conditions, which mean that this is 0. So all these vertices on the boundary are just equal. The value there is equal to 0. And this gives us a well-defined field. And we also had a random walk representation of the covariance. So the covariance for this field is the same as a green function of a simple random walk. Up to the exit time. Actually, to be precise, up to the exit time minus 1 of that. Okay, so that's our model, and we are interested in the maximum. So I will slightly deviate from the notation I used yesterday, and I will denote by xn star the maximum of xv n, where v is in Vn. And note that my field is always indexed by n because although the density is the same, there is a Dirichlet boundary condition. So for different n's, you have Dirichlet boundary conditions in different subsets, and therefore the field is a different field. So one consequence of the random walk representation is the following lemma that I will not prove, which is the following. If I look at the so one last thing is that I will always write for the covariance R. I just want to make sure that I'm not confusing notation, so please hold on for, yes. So Rx or Rxn of xy is just the expectation of xxn xy or vw xvn xwn. Okay? So every time for any field, if I write R, I mean the covariance function. And the lemma is, this gives us an easy way to compute covariances, and from it, and some basic exercises in random walks, you can deduce the following, that Rxn of Vw minus 2 over pi log n minus log of V minus W 2, this is a 2 norm, this whole thing, this thing. So this difference is bounded by a universal constant. So this means that the decay of correlation is logarithmic. That's really what I wrote here. And it's not surprising, right? Because that essentially corresponds to the following fact. If I take 2 points, the decay of correlation is essentially the probability, if this is my point x, or v, and this is my point w, the way to compute the covariance is simply to compute the probability to hit w before exiting, multiplied by the green function at w. Right? Because that's what the Markov property and this formula tell you. And the probability to hit w before hitting v is logarithmic in the distance. So all these facts are not too hard, and you can do them by using a simple random walk. And also from here, you know that the maximal covariance is 2 over pi log n. So that's the maximal variance, so it's 2 over pi log n. Good. So now we are ready to the first real result. So maybe, yeah, let me write it here. So proof here is simple random walk representation. And now we have following theorem. So so let's take d greater or equal to 2 and define, actually d equal to 2, I don't know why. And define Mn to be what we expect, namely, let me just copy it, is 2 square root 2 over pi log n minus 3/4 square root 2 over pi log n. And this number should really be written like that, which would be the standard normalization. And okay, so that's Mn. So the theorem is that the expectation of the maximum is less than or equal to Mn plus order of 1. So that's one point. And the other point is a law of large numbers. The expectation of xn star divided by Mn goes to 1. So of course, when I divide by Mn, writing this term or not writing this term doesn't make any difference. So for the law of large numbers, the log n term doesn't play any role. The reason I write it is because of item 1. Okay? Good. Good. So there are 2 items here. I'm sorry for those who couldn't see it before. The first item is an upper bound up to order 1 on the expectation. The second item is a law of large numbers. And this convergence is in probability. Okay. And finally, of course, you can apply Borel's inequality. Once you have something about the expectation, you can apply Borel's inequality, and it gives you whatever it gives, which is some fluctuations of order maximum of square root log n. Questions? Oh, okay, yes, I wrote expectation, but as we will see, in fact, it's also in probability. You can erase the expectation. You will also have convergence in probability. So maybe I should say also xn star divided by Mn goes to 1 in probability, although we will show much better later, so I'm not emphasizing this right now. Okay. In fact, once you know that, Borel's inequality gives you that for free. Okay? Because Borel's inequality tells you that the fluctuations are at most like the maximal variance, which is the square root of the log. Okay? So that immediately gives you what you need. Okay. So it will turn out if we just wanted a law of large numbers and wanted first the upper bound is trivial. Exactly like it was for branching random walk. So upper bound in 2 is trivial. Just use union bound. So we have n square points, n square random variables, times the probability that xv is larger than mn times 1 plus epsilon goes to 0. This is just a Gaussian random variable. You stick into here the tail estimates for Gaussian random variables, you get that for free. So the upper bound in the law of large numbers is trivial. This, of course, does not yet give what is written here, but it gives that fact. Is that okay so far? Yes? No? Questions about this part? Because this part is really the easiest. Okay. Now we are going to use some of the tools we prepared before. So we want to show both a lower bound and a sharper upper bound. So to show a sharper upper bound, what we are going to do is to compare with the Gaussian free field. With branching random walk. So that's an important observation that I want now to make. Namely, what is the relation of branching random walk in all this story? So let me now describe the branching random walk as a story on this particular graph. How will we do that? Well, we'll do the following. Take this graph, take this box. This I will call level 1. So the whole box Vn, I'm going to do it for Vn, which is 2 to the power small n. We will see later that it's enough to only consider such Vn's. We will see that in a moment. But for the moment, let's assume this. So this I will call level 1 of my construction. And I will attach to this box, the box Vn, I will attach one random variable. Let's call it x1. Not x is taken, so let's call it a1, which is normal 0, 1. In level 2 of my construction, I'm going to divide the box in 4. And to each sub-box here, I'm going to attach a Gaussian random variable, normal, 0, 1. So let's call this A21, A22, A23, A24. And then I continue. So in the next level, I'm going to divide each of these squares itself by 4. And then I will have A31, A32, maybe here I'll have A33, A34, a total of 16 independent Gaussian random variables. So by doing that, and because I took n to be 2 to the power n, I do this for n stages and I exhaust the whole box. So at the end, I have a sequence of partitions, finer and finer partitions of the box, and to each part I attach the Gaussian random variable. Now, to any vertex in the original box, so for any vertex in the original box, so let's call it, we are going to define a field, let's call it SV. This is going to be the sum of Aij over all I and j such that the box covers V. Okay, I'm sorry if it's not clear what I wrote here. So this is just summing up for every point in the box all the random variables that belong to the boxes covering it. So at level 0, all of them will get A1, but then this point will maybe get, so maybe I'll do a point here so it will be clear. So this point will get A1 plus A21 plus A31, and so on. Okay? And now it's clear that this is a branching up to labeling of the vertices. This is just a branching random walk. Because what are we doing? You can, this construction give a hierarchical labeling of my vertices in the box, but the construction of the random field on this, with this labeling is just branching random walk. Except there are now 4 children and not 2 children for every father. Okay, so in fact it looks like that. This is A1, this is A21, A22, etc. Okay? So that's just another way to represent branching random walk. Now, what is a covariance for this branching random walk? So if I take 2 vertices on my square, the covariance between them is determined by the tree distance between these points, which is a hierarchical distance between these points. What is the relation of the tree distance to the Euclidean distance? The answer is that in general, up to some constants that come from edge effect and discretization effect, and from the fact that here I don't, where is my, if you look at the formula up there, there's a constant error over there, but up to constants, the distance, the Euclidean distance is bounded above by the tree distance. Why? Because if you take 2 points here that are very close in Euclidean distance, okay, so actually the best way to see it here, these 2 points here are very close in Euclidean distance, but they are very far on the tree because I've split on the first generation. Okay? So this means that we have a direct comparison between the distances. The tree distance is larger than the Euclidean distance, which means that we have a direct comparison of covariances. The covariance of this field, okay, is dominated by the covariance, is dominating, sorry, the covariance of the GFF. Okay? Up to a constant, but this constant I can always fix by adding one more level here, one more child to the bottom layer.
Sorry,
yes?
Question. The top leftmost vertex and the top rightmost vertex.
Yes?
I have a Euclidean distance of order 2 to the n.
No, small n. So the distance is, okay, no, thank you.
Euclidean.
Thank you, yes, but, okay. I understand, but I should have written log. Of course. Everything is here on this logarithmic scale. So this is a small n. Everything is small, is in a logarithmic scale. And we measure distances in this hierarchical distance. Thank you very much. Okay? Because the distances here are, the maximal distance on the tree is a number of levels, which is small n. Okay? You look at unconvinced. Why? This is a positive thing. This is n. No, 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 no. I didn't rescale anything. This is always larger than 1, the Euclidean distance. And nothing here is rescaled. Okay? So this is really a box of size n, which is 2 to the n. So the maximal distance is indeed small n. And of course, there is also a multiplicative constant. The same multiplicative constant that we have running around all the time. This square root of 2 pi is multiplying everything here. So, okay?
But I don't understand. If the tree distance is larger,
Uh-huh.
the correlation will be there faster, right? So
If the tree distance is large, this means that they are almost uncorrelated.
Exactly.
Yes?
And that's why the correlation on the tree is less than.
That's correct. But the covariance, that's correct. The correlation on the tree is less than the correlation. If I said something else, then I don't know what I said, but the correlation on the tree is definitely, it's more independent. Okay? Things on the tree are more independent. And now we remember the Sudakov-Fernik comparison. And the Sudakov-Fernik comparison told us, essentially, that if things are less correlated, the maximum is larger. Okay? Therefore, the expectation of xn star, and let me put here a tilde to remind us that we multiply by square root over 2 pi or whatever, so that the normalization of the variance is of the same, with the same constant. This will be smaller than the expectation of Sn star, which is a maximum. Actually, with my notation, I wrote it like that before, which is a maximum of a 4RE3 branching random walk. Okay? So this gives me the upper bound. This gives me the first point. Now, why plus order 1? Because I've cheated a little bit. Because I had to, because this was true only up to a constant. Or actually, this may be, well, actually, this is true up to a constant, and also in the covariance, I have a constant, so the whole thing is up to a constant. But adding a constant is like, for the tree, it's very easy to make sure that the actual tree has a bigger distance, simply by adding here several levels of independent Gaussian random variables. And so you will compare not with the tree that ends at level n, but with a subset of the tree that ends at level n plus 5. Okay?
Sorry, which is for the Gaussian free field and which is for...
This is a Gaussian free field. X is a Gaussian free field, like in the theorem, and S is a branching random walk, like here.
But we just concluded that the correlations on the tree are less.
That's correct. So it's more independent, and no. Look back into Borel's inequality, into Sudakov-Fernik, and you will see that the more uncorrelated, the way to remember it is the following. If you have IID random variable, compare IID random variable to a situation where all random variables are the same. Make this comparison in your mind. So if you have IID random variable, you have many more chances to be large than if you have a single random variable. Okay? So always, if you have more correlation, you reduce the expectation of the maximum. And that's the direction of the inequality. Okay. So this is the upper bound here.
And why do we have tilde there?
Sorry? The tilde is just a constant multiple. That's what so x tilde v is just xv multiplied by, I believe, square root of pi over whatever you need. I don't remember what it is, so that the variances match, the leading order of the variance match. Otherwise, of course, you cannot compare. Okay, and you can see that in the expression there, you have 2 over pi. This tells us that this should be 2 over pi. Okay? Good. Other questions about that? Okay. How do you do the lower bound for the law of large numbers? So the lower bound for the law of large numbers. So what we are going to do, we are going to dilute the tree in such a way, to dilute the GFF so that it is comparable in covariance to the Gaussian free field, up to a small multiplicative factor. Okay? So what are we going to do? What we are going to do is, let's explain it on the first level, and then I will not write anything more. Other questions? Okay, so what was the difficulty? The difficulty, say, at this level was with points like that. Okay, that somehow on the trees are very far, but on the Euclidean space they are very close. So what we are going to do is we are going to not take such points. Make sure not to look at such points at all. We want a lower bound, so instead of taking the maximum of the Gaussian free field over all vertices, we are just going to take the maximum of the Gaussian free field over some vertices. And the some vertices we are going to take, it's very simple, we are going to take a square here. At the first stage. So all the vertices outside of these 4 squares, we are not going to look at them. Okay? Then at the next stage, we are continuing. We are going to throw away vertices, except for these guys. Actually, my picture is somewhat misleading.
So what's the size of the squares? Comparable?
It's comparable to the big size, so that I lose a factor 1 minus delta at each stage. Okay? So, indeed, I essentially do that. Okay, and this is 1 minus delta. So this is, in this example, this will be n half times 1 minus delta. Yes, my picture before, I agree, was somewhat misleading. And then you continue doing that. So you look only at vertices that correspond to this construction. And it's easy to check that for such vertices, the distances are comparable, because this problem that we had before doesn't occur. Now, 2 vertices, one vertex that is here and one vertex that is here, they do differ by a constant multiple of n, which means after you took the log, by just a constant. Now, you do that for n stages, so you lose 1 minus delta times small n. So this is a multiplicative factor on the variance, which is of the order 1 minus delta. So now you can compare the distances with a multiplicative factor 1 minus delta. So this means that you can get that the expectation of xn star is greater than the expectation of the maximum over v, which is good, or maybe I should call it delta good, of 1 minus delta times SV star. Sorry, so the over good V of XV. So that's the first step. You take only some of the indices, not all of them. And then you compare to the tree, and you get that this is greater than or equal to S star V, S star N times 1 minus delta. You have less generations to do. You have less points, less generations. Right? You throw a...
These generations, they all are still alive.
Sorry?
Do you mean that until this generation, actually all descendants are still alive?
All this, so I compare the correlation of the guys that I took here for all these many generations. I compare it to just a branching random walk with this many generations. And this is comparable, and this gives the lower bound. Again, by an application of Sudakov-Fernik. So that's actually not done in this way. This was first observed in a paper of Bolthausen, Döschel, and Giacomin about 10 years ago. I'm not giving more details for many reasons. The main reason is that we are going to do better in a short while. So I'm just giving you here a sketch of what you should do if you want to do just a law of large numbers. Now, we are actually interested in maxima and fluctuations of the maxima. So obviously, this result is good at the level of law of large numbers, but not better. And in fact, the proof of Bolthausen, Deutschel, and Giacomin was not done this way, but was using also a certain tree structure and the Markov property of the field. Okay. So how can we do better? So I remind you what were the steps for branching random walk. We first had a law of large numbers. Then we said, once I have a law of large numbers, at least on subsequence I had tightness. And we had this Decking-Host argument for showing that. So I want to show you how the Decking-Host argument applies here, because here it's less obvious. So theorem, or lemma. So this is Decking-Host argument revisited. The lemma is the following. The expectation of the maximum of two independent copies of the Gaussian free field is less than or equal to twice the expectation of that. Okay. We already saw that once we have an inequality like that, if we control the right-hand side, then we are done. Then we have tightness of the maximum. Fluctuations are of order 1. Because this is greater than the expectation of chi n star minus the expectation of chi n star. By applying Jensen and conditioning on the y. So we have this inequality, and I want to prove it. So before I prove, I want a remark. The expectation of x n star is increasing. Proof. Let's take the field in a box of size n prime, which is larger than n. This is a Gaussian free field in a box slightly larger than n. Let's take now a box inside of size n. Okay? Let's decompose x v n prime for v in Vn in this smaller box. Okay, we can write it, we saw that last time, we can decompose it in the sum of two terms. One is a Gauss, so this is equal in distribution, this field is equal to distribution, in distribution to the following. A Gaussian free field in the box n, plus a field which corresponds to the conditional expectation given the boundary values. Is that okay? You remember this decomposition from yesterday. So we have a sum of these two fields. Both are zero mean, and they are independent. Okay? So we saw that if I have a sum of two independent fields, the expectation of the maximum just increases. So this gives me that the expectation of x n prime star, which is of course larger than the expectation of the maximum over these v's, this is larger than the expectation of x n star. Okay? So it's monotone. In particular, in the lemma that I had, I said we are going to prove things for n, which is 2 to the power n. Now you see that it doesn't matter. Because the distance between n between 2 to the power n and 2 to the power n plus 1, the distance in mn is just a constant. So it can be absorbed in everything. So once I proved the upper bound for the dyadic, for this power of 2 sequence, I have it for all. Okay, so that was my remark. And because of this remark, I'm going to consider from now on only n, which is a power of 2. Okay, so now we'll do the proof. And you can already kind of imagine the proof. So let's take the proof. Here is my box of size 2n. So I'm going to split it in 4. So that now I have boxes of size n here. And now I can decompose my field. xv2n is equal to xvin plus yvn. I will explain in a moment. So let me explain that. That's the decomposition we did before, where what is yvn? Yvn is just the composition conditioning on the values here. So I use a Gaussian decomposition in terms of conditional expectation plus a field, but my conditional expectation is with respect to the variables that I drew here. Okay? So yvn is just the expectation of xv2n condition on sigma of x u in, okay, u in those lines. Okay? So I condition on the values here, and I write my field as something plus the conditional expectation. Because of the Gaussian decomposition, these two guys are independent. Because everything was zero mean, both this and that are zero mean. Now what are these guys? What are I, first of all? So I just correspond to I equal 1, I equal 2, I equal 3, I equal 4. So I wrote it, I prefer to write it like that. Why is that? Because once I conditioned on that, what is happening in those 4 boxes is independent. And the field that is written here, what is it? It's exactly the Gaussian free field in the smaller box with 0 boundary conditions. That's also what we said. We take a Gaussian free field in a big box. We condition on the value on the boundary. What is inside is the sum of a conditional mean plus a Gaussian free field in the smaller box. Okay? So now we are done. Because the expectation of the maximum of xv2n, which is just the expectation of x2n star, that's how we defined it. This is first greater than the expectation of the maximum of xvi n, because these are independent. So this is equal to the expectation of the maximum over I equal from 1 to 4 from 1 to 4 of xvn, the maximum over v in vn of xvn I. So we have 4 copies of this Gaussian free field. So I can write the maximum as a maximum inside each box and then the maximum over boxes. which is clearly greater than the expectation over the maximum of x n star I. By this I mean independent. And now we apply the Decking-Horst trick. So the maximum of A and B is equal to A plus B plus the absolute value of the difference. So this is equal to the expectation of xn star plus the expectation of xn star minus xn star prime divided by 2. And this gives me the inequality. Okay? So we have shown that we can adapt the Decking-Horst argument to our situation. Questions about that? So this part used the Markov property in a crucial way. The previous proof actually did not use a Markov property at all. It just used a covariance. But this part uses a Markov property in a crucial way. Okay, good. So what are the conclusions from that? So the first conclusion we can immediately derive is the following. So conclusion, or corollary, and this was observed by Bolthausen, Döschel, and myself a couple of years ago, a year and a half ago. What you conclude from that there exists a subsequence nk, or nk, deterministic, such that xn star minus e of x and k star, this is tight. So this is a sequence of random variables in k, and this is tight. Yeah? Same trick. As soon as you have this domination and the law of large numbers, you get this inequality. You get this tightness. Okay, so that's the first corollary. And the second thing is that, in fact, to show tightness, on full sequence, we only need that the expectation of x 2n star minus the expectation of x n star is bounded by some universal constant. Because once we have that, then the lemma tells us that we have tightness. The other direction that this is positive we already showed. Okay? And in this situation, we also remark that the upper bound was the expectation of xn star was less than or equal to mn plus a constant, and m2n minus mn was bounded by a constant, because the leading term was log, and the second order term was a log-log, which doesn't change when you move from n to 2n. So if we could show a complementary lower bound, which is with mn, then we would be done. Now, the complementary lower bound that we showed was not with mn, it was with mn multiplied by 1 minus delta. So certainly, with such a bound, you cannot hope to show this. So we need to do something else. Okay? Is it clear where I'm heading now? So the next step will be, of course, to show that. So what is missing is a lower bound on Mn, which is of the same order. So our next goal, therefore, is to show that the expectation of Mxn star is greater than or equal to Mn minus a constant. Then we would be done. As long as this constant does not depend on n, we are fine. Questions? Yes?
Is the middle point of the same order as the maximum, the middle point of the box?
No. So the middle point of the box, first of all, it has mean 0. But second, the variance of the middle point, so, okay, good question though. So the middle point has a variance of, say, x n half was log n, right? So small n, up to a multiple constant of this order, right? So this means that the typical value of the midpoint is like square root of n. But the maximum is like n, like small n. So the maximum is much larger than a typical point in the middle, which is not surprising. If I have lots of random variables, each one is of order square root n, there is no reason that the maximum will be the order of the typical one. For that to happen, they have all to be very strongly correlated. And that's not the case here. Okay? Did I answer the question? So this is of order n, and while the expectation of x n star is also of order n. We will show. We have not, well, what we have shown is that this is greater than 1 minus delta times the constant. So certainly it's much larger than the typical point in the middle. Okay. Now, why did we get such a lousy bound on the expectation of the maximum? How did we get a bound on the expectation of the maximum at all? We compared to the branching random walk, and this comparison was not good, because the branching random walk has all these discontinuities with respect to the Euclidean method. So the idea now is to refine this comparison. So let me do that here. So I should call it towards the lower bound. So the lower bound, I mean the expectation of xn star greater than mn minus a constant. That's what I want, but I have not shown it yet. So I want to have some field that has the following two properties. First of all, it retains the global picture and also the local picture of the Gaussian free field so that I can do comparisons. But on the other hand, it is simple enough that I can actually do computations. Okay? So remember, for branching random walk, we did computations, we exploited second moment, we exploited a lot of independence in the second moment. So, how will we do that? Well, let's remind ourselves of this hierarchical construction that we did. What did we do in this hierarchical construction? So this was a stage 0. We had one big box. And then in stage 1, we had these 4 boxes. And already here, we created a disaster. Because 2 points here that in reality are very correlated, in my branching random walk picture, they were uncorrelated. How can we get around this point? Well, here is how we're going to get around this point. First of all, we are going to work on a torus, just to make things simpler. So if we look at, remember, I'm trying to prove the lower bound. And for the lower bound, I can work on a bigger box and just look inside a smaller box if I prefer. And so I can always put myself in a subset of my big box. And then it shouldn't be surprising that if I close things on the torus, it should look similar. So I'll explain in a second what I mean by working on the torus. But the description I'm giving you now is, think of that not as being a box, but being a torus. And now we are going to do the following thing. Instead, at this level, I'm now at the first level. Instead of just looking at these 4 squares, I'm going to look at all possible shifts of these squares. So this is an example. Here is one shift. I know that you don't see the colors in the back, but I hope that you can just guess what I'm doing from. And here is another one. And here is maybe a third one. And this is what I meant by the torus. Okay? Okay, is that clear? And of course, I also have, for example, I don't know, this box. Something like that. Okay. Okay? So I have all the shifts of such boxes. This gives me a collection of boxes at a given scale. It's a scale, in this case, the first scale of the construction. And now I'm going to attach to each of these boxes one Gaussian random variable, of course not of variance 1. That's the key. To each such box, I'm going to attach a Gaussian random variable whose variance is exactly the number of boxes that cover an individual point. So if the side of this box is 2 to the power k, eventually, there are 4 to the power k boxes that cover an individual point. So to each box at level k gets an independent Gaussian, centered Gaussian, with variance (4 to the minus k). Okay? And now I define as before, let's call it a field ZV to be the sum. So this is a random variable, let's call it BK V. Not V, BK B. So B is an index over boxes, and K is a scale. Okay? And now I'm going to define, and we are going to define our ZV to be the sum of BKB over all boxes B that cover X, that cover V. So this part of the definition is exactly like before, except that now I have many more boxes. I have many more random variables to contend with. Before I had exactly 4 to the power n random variables. Now I have many more random variables involved. So some observations about this construction. Questions, first of all, about this?
What is, sorry, just slightly misleading of the, what is B in this index?
B index is a box. So, yes, so let's call this capital B, and then it will be less misleading. Capital B is a Gaussian random variable, and the small b is just the index of the box. Okay? Thanks for this. So now we have this construction of a field, and I want to make a few comments. So the first comment is that the contribution at each level to a particular point is exactly as before. So the contribution to V from level K is distributed like normal 0, 1. That's how I rearranged everything. And it's IID between scales, independent between scales, because that's what I did in my construction. So that's independent between scales. So this is, in that respect, it's the same as branching random walk. That was definitely the case in branching random walk. The second point to note, and still in a qualitative way, is that there are no discontinuities. What I mean by that is that now things, distances or covariances are smooth in the Euclidean distance. Because in fact, they are a function of the Euclidean distance. Everything is here a function of the Euclidean distance. Okay? So we have no discontinuities. And in fact, we have the following fact. Maybe I should write it here. The third point is that if we look at the expectation of ZV, ZW, okay, so this correlation is larger than the same thing for the Gaussian free field, so XV. Actually, let me write it in the way we are going to use it. No, like that. This is the direction I want. It's comparable. In fact, we actually have that. But the direction I care about is the direction I said before.
We have correlation in Z depends not on the Euclidean distance, but actually on the distance with square box, yeah?
Yes?
The correlation is number of boxes.
Yeah, but remember that we care only about the log. Right? All the distances, all the things that we care about is the log, is the scale. So in the log, there is no difference between a square box, a round box, okay? Okay? Because, again, the log is the important thing here. We are really measuring things in hierarchical way. Okay? But you are right. If everything was proportional to the actual Euclidean distance, then I would have to worry about square boxes, round boxes. Maybe I would do a different construction. But that's not the case here. Okay. So this expectation is related to the log of the distance, and we have this kind of control. So this means, and I'm cheating here a little bit, I'll tell you where, from this we will deduce eventually that the expectation of the maximum of the Z field, so I hope the notation are clear, this is the maximum of my Z field of my, by the way, we call that the modified branching random walk. So Z is just a modified branching random walk, and the expectation of that is going to be smaller than the expectation of X n star plus a constant. Now, here I'm cheating. Where am I cheating? So the Sudakov-Fernik inequality does not allow me to compare up to a constant. I really have to have domination. I cannot say if one is up to a constant, because up to a constant might mean I added an independent random variable to all vertices, and then the maximum over this independent random variable could be huge. So I certainly cannot claim that if I have Sudakov-Fernik up to a constant, then I have that up to a constant. That's not true in general. We need to do something. But what we do is exactly like I said before. Namely, we take a little bit more or a little bit less levels. We don't go all the way down. We go only all the way down up to a finite number. And then we actually do a precise estimate that says, if you go not all the way down, but a certain number of levels before that, you can eat up any constant here and actually get actual domination. Okay? So I'm not proving that because that's technical, but this is just to emphasize that this implication is only approximate. There is a little bit of work to do in comparing modified branching random walk in different scales, where by different scales I mean you just erase a finite number, the last finite number of scales, and for some other reasons you have to actually erase a few levels from the top. But these two things are not a big deal. So now it remains to estimate that. So after we did all this work, we had a comparison. All that remains to do is to compute the expectation of the maximum of this modified branching random walk. So let's look slightly more closely on the branching random walk. And remember that I'm going to do things. I only care about the lower bound. I don't care really about the upper bound. I only care about the lower bound. So we want to show that the expectation of Zn star is greater than Mn minus a constant. That's what we need to show.
Sorry, have you defined the free field as a torus
No.
now?
But that again is coming to this story that I said, that instead, if I'm looking at lower bounds, I don't have to take maximum over all points. I can take maximum over points in the middle.
Does this variance comparison hold if you don't take periodic boundary conditions?
There is nothing in periodic. I never discussed the Gaussian free field on a torus. The only place where I discussed the torus was for the modified branching random walk. So my Gaussian free field is always on the box with Dirichlet boundary conditions. Okay? And then what I said is that I look inside a box of size n½ say, and I do my comparison of covariances between this guy and the box of size n½ in the modified branching random walk. Okay? The torus is just a convenient device to define the modified branching random walk in a way that you see that everything is proportional to the distance. But I'm getting away from the boundary anyway. So if you preferred, you could have defined that not on the torus, but actually on the original square with some truncation. It wouldn't make any difference. I only care about what happens here. Okay? Yeah. But that's a good point. I mean, I never defined what it means, a Gaussian free field on the torus. This by itself is not well defined, right? Because we have to anchor the field somewhere. We cannot, it's not like an Ising model. We cannot put boundary conditions which are periodic and forget about it because we have to anchor the field. Otherwise, it would be shift invariant and it would not be defined. Okay, so this I didn't do. Okay, so we want to show that. And to show that, we need to do first moment, second moment. Now, I'm not going to bore you with that, certainly not when I only have 25 minutes. But let me make the following observations. So if you look, what does it mean? I have to look at an individual point, right? I have to do a first moment. So the first moment on the tree, what was it based on? It was based on saying, well, let's look at this ray and just ask a particular event, namely the event that we are all the time below the straight line. That was my event that I took into the computation of the lower bound. I emphasize, I'm dealing here just with the lower bound. So this I can do here, and there's no difference. All probabilities I computed for branching random walk are true here because it was just a computation for sums of independent random walk, independent random variables. So it was just estimates for random walk. There was nothing special about, there is no distinction at the level of an individual vertex between branching random walk and modified branching random walk. So the only thing we have to worry about is the second moment. So the first moment, as I said, is like branching random walk. There's really no difference. So the first moment in lower bound proof. So you define the random variable, which was the sum of the indicator of these good events, BV or AV, I think I called them. This was my good event, and you just, exactly as before, show that the expectation of this guy is large enough. Okay. What about the second moment? In the second moment on the tree, we had two vertices. And what did we do? We said the probability of this event happening, we essentially needed to compute the probability of AV intersect with AW. The event AV, I remind you, is just the event that you go to below the straight line and you end where you want to end. That was the event AV. Okay? So now we have two vertices, and in the case of the branching random walk, we had complete independence. Namely, this was independent from what happened later, and then what happened here was independent of what happened here. So by just conditioning on the value here, we could finish the proof. Okay? What happens for modified branching random walk? Well, for modified branching random walk, first, there is some smudge going on at this point. Because when we are exactly at the scale of the distance between 2 points, we have lots of overlaps. But if we go to finer scales, we again recover independent. Right? So if we look at the modified branching in this picture, and we have 2 points that are at a given distance, once I go to scale, which is smaller than half the distance between them, there is no overlap. Okay? So what happens in the bottom, the analog of the bottom here, is completely independent on these two guys. Is that clear? Now we have to deal with the top. And the top, what is a big difference? Here, the influence of the top level on this guy was exactly the same as it was for this guy. Everybody agrees with that? It was exactly the same. But in our situation, that's not the case. Because the contribution, say, from the top or the second to top level on this guy is correlated but not identical to the contribution to this guy. Because there are different balls involved, different squares involved. But we definitely can write that, so let's look at the contribution to V from scale K. So we can write that x, or how did I call the modified zv, is the sum of zvk, sum over k. So this is a contribution from different scale. And zw is the sum over k of zwk. What I said before is that for k smalls, these z's are independent, if the k is smaller than the distance. For k large, namely for k's that belong here, we can write zwk to be zvk plus a small error, plus an error. And what we really need to do now is to control the size of this error. What is the maximal error of this field among all points in the square? Okay? Or between 2 points, whatever. And here, to control the error, what you can show is that the variance of the error is of order 1. That's easy, because essentially everything happens near this fudge region. When you go very far up, the overlap is almost complete. And you can also show, and this requires yet another tool from Gaussian field theory that I did not introduce, you can also control the maximum error. In fact, the mean of the maximum error by an entropy argument. So this is something I don't have time to get into, and it's actually not very hard. It's essentially saying that if I have a very correlated field, and this field is going to be very correlated, the expectation of the maximum cannot be too large. Once I control the expectation of the maximum, because the variance is of order 1, Borel's inequality gives me control over the maximum itself, and actually the tail of the maximum. So the only issue is to control the maximum of this error I'm making when I'm doing this comparison, and this is controlled by an entropy. And as I said, I'm running out of time, so I don't want to get into this actual control, and also it's pretty technical, so I don't want to do that. So once you do these 2 steps, you are done. Because now you can apply the second moment method. You have essential independence as we had before. You do the computations for simple random walk, and you conclude by the second moment method that the expectation of Mn, expectation of Zn star is greater than the expectation of Mn minus a constant. So this leads us to the following theorem. That if we take GFF on Vn, then E of Xn star minus E of Xn star is tight. And the expectation of Xn star is Mn plus order 1. Okay? So I gave you most of the steps except for this one, which is actually detailed in the notes. If you care about it, it's maybe 2 pages of computation. It's not a big deal. Okay. So that's it for the tightness. And now questions and problems and links to other problems. So the first thing I want to mention is that there is an obvious question, which is convergence. Namely, does this quantity that I wrote here, I wrote and erased, no, I wrote here, does this quantity converge in distribution to anything? And this is completely open, and the techniques I have discussed so far give you essentially nothing on that. So an easier question, maybe still with convergence. For branching random walk, I told you that there is a convergence, there is a limit law, which the essential element of the proof is to obtain very sharp tail estimates on the distribution of the maximum. So as it turns out, if you have, because of the independent structure of the tree, if you have very good tail estimate on the distribution of the maximum, you can translate it to a statement about convergence. So this leads to, motivated by that, you can also ask about tail estimates. And for this, there are partial results, which are not as tight as the ones that allow to prove convergence, but they are already a good deal in this direction. So note that the proof I've shown you gives you essentially nothing in terms of tail estimates. It even doesn't tell you that the variance is bounded, the variance of the difference. We used comparisons. We essentially just computed the expectation. We used this decking horse trick, and we only showed that the expectation of the difference of two independent copies is bounded. We didn't say even that the variance of that difference is bounded. But in fact, Ding has shown that by using this sinning type of argument that I said before, namely taking a sparse subset of points, not looking at all points, but looking at a sparse subset, you can get tail estimates. So this is in particular, the upper tail is like for branching random walk. So the probability is that Zn, not Zn, xn star minus mn greater than y is asymptotic, or no, is greater or something like that, not with the same constant. So the upper bound and the lower bound are not with the same constant.
Can't you get this just by sit-down inequalities?
Excuse me?
Why can't you get the same just by sit-down inequality?
Because we don't have Slepian's inequality, because a crucial element of Slepian's inequality is that the variances are equal.
Okay, but if the variances are even...
So if you were dealing with a variant of the problem in which the variances are equal, and there are ways to define Gaussian free fields like that, which I did not discuss at all, but maybe if you ask, I can mention it now. So instead of taking the green function representation as I did here, which is the time of exit from a box, you can look at the torus and look at an exponential killing time.
Okay.
So I'm answering your, so then you would get a stationary field, and then you can compare it to branching random walk, and you would get that for free.
Instead of using literally the principle is that even if the variances are not equal, you can compare not only the expectation of the expectation of the maximum, but the expectation of all increasing convex functions of the maximum.
No, because then you would be able to compare the maximum. No, that's exactly where you need the conditions that the variances are equal. We can discuss it later, okay? Let's discuss this later. This is exactly the point where you need the condition of equal variance. Otherwise, you would not need, otherwise you would say that Sudakov-Fernik is enough to conclude that the tail of the maximum is dominating one the other, and this I can show you is not true. These are examples to show that this is not true. So, okay. So, this is tail estimates, but the lower tail is different. And the lower tail is of Gumbel type. So it's e to the minus e to the minus cy for y negative. So the probability that xn star minus mn is less than minus y is something like that. And probably if I write it like this, I should write this for y large. And this is very different from the tree. On the tree, on the branching random walk, if you think about it, there's a very easy way to make the maximum small. How can you make the maximum small? You simply make these two guys small. And this is only a Gaussian cost. So with a Gaussian cost, you can make the maximum small. But for the Gaussian free field, that turns out not to be the case. Okay. The second thing I told you that was done for branching random walk is the genealogy of the collection of maxima. And this we do not have for the branching random, for the Gaussian free field. But we do have some new results on, so maybe I should say, and not detail them. So there are results on gap between first and second maximum. So it's not too small and it cannot be too large. Sorry? Order of 1, of course. Yes, yes, it's order 1. But there are tail estimates to say how big it is and how small it is, but it's of order 1. And there are... Okay, so maybe that's all I want to say about that. And in the last 5 minutes I have, I want to mention a connection with cover times, which is actually how I got into this story. So, maybe Yuval will speak about this, Yuval Perez will speak about it in more details next week. There is a very general connection that relates local times and maxima of Gaussian free field via isomorphism theorems of the type that actually were hinted in the talk of Yves Lejean. But I don't want to speak now in this generality, I want to be concrete. So here is a concrete problem. Take the two-dimensional torus of size n. Start a random walk in the middle. Look at the time until you cover every single pixel in this picture. So think of it as a screen. You have this random walk. How long will it take before the whole screen goes black? So call this time Cn. This is a cover time. And about 10 years ago, Dembo, Perez, Rosen, and myself proved a law of large numbers for Cn. Namely, Cn divided by n squared times log n squared converges to a constant, and I don't remember the constant except that it has 2 and pi in it. And the proof essentially was the same. Okay, you need some imagination to see that it's the same, but essentially it was the same as the one I described for you for the upper bound of the Gaussian free field. Namely, you take your square, you look at, if you start to do a second moment method, namely you start to look at points that have not been visited, you measure that by looking at excursions between concentric circles. And somehow, once you tell me that you have an excursion, how many excursions you had here between concentric circles, then you don't care what you did here in terms of what is happening inside. So you have a very natural hierarchical structure that is almost a tree, but it gets fuzzy when the concentric circles start to be the same for different points. And then again, when the scale is much larger than the distance, the concentric circles are essentially the same for this guy and this guy. So you are morally in a very similar situation to what you were in the modified branching random walk. Except that this is only a law of large numbers. So this construction worked very well for the law of large numbers. And in fact, what you expect, by analogy with this picture, what you expect is that the cover time divided by n squared, this quantity, but actually not this quantity. The square root of this quantity is tight. Because if you do the story that I just told you with the excursions and you write it down, this is really the analog object. This object, the story of excursions, is related to the square root of this object. What is the linear profile is for this object. Not for the cover time, but for the square root of the number of excursions. So you expect this. And this I want to state as an open problem. This is open. And this is true on the tree. So on the tree, you can ask the same question. What is the cover time of the tree in terms of the depth of the tree? And there is an analogous quantity, which is a cover time divided by the number of vertices. And this turns out to be tight. This is not the order of the maximum. There is this log term. So exactly like with the maximum, we forget about the log term and we ask whether the quantity is tight without dividing by the log term. So this is true on the tree. However, the correction term is different. So by correction term, I mean the 3/2. The 3/2 for the cover time on what should have been 3/2 for the cover time on the tree turns out not to be 3/2, turns out to be 1/2. For reasons that I can explain to whoever is interested, but I will not now. So there are analogies between these problems, but they're really not the same problem. And in any case, in the context of the cover time of the two-dimensional torus, the question is widely open. How tight are the fluctuations of order 1? Okay, I've exhausted my time. I wanted to tell you more about this connection with cover times, but that's it. Thank you.